Okay, AP Chem kids. Um, Today I just want to do some review for Unit 2. Um, and so this is kind of be kind of part stoichiometry, part kind of visualizing what's going on, why it's important to be able to come up with the overall balanced equation for a chemical reaction, but to actually get the net ionic equation. And then also visualize what's going to happen. So this is going to be a lot of this a little bit of solution stoichiometry practice, but really visualizing in a very simple way. Like so, visualizing the chemical reactions before and after, before the reaction, after the reaction, and what you would actually see and maybe even smell during a chemical reaction that takes place in an aqueous system. So, dissolved in water basically. And so I think it's important to be able to visualize that. So, again, this is overall kind of a review of all Unit 2, if you want to think of it that way. And there'll be a similar type of question, and it'll be worded similarly on your unit test. And so, this is just, to help you review with overall everything that we've been doing in Unit 2. Okay. So again, let me just show you what the type of question I'm talking about. So, these, I made a video before on solution stoichiometry, and this was a sample question that we did. And so, it says 50 milliliters of 0.75 molar solution of magnesium hydroxide, solution aqueous, is mixed with 50 milliliters of 0.75 molar solution of aluminum nitrate aqueous. And you have to answer all the, normal questions. But really, to really understand how you're going to answer these questions, especially, what are the resulting concentrations of everything after the reaction takes place, it's really important to kind of visualize what's going on. What are you losing? Are you gaining anything? What's being lost? What are you going to see during the reaction? And what will my reaction vessel look like at the end of the reaction? All right, so again, it's important to visualize, and so that's what I want to do here. So let's do some practice, and I'll show you what I'm talking about. Hopefully, it makes sense to you after you see it. Okay, so I titled this lesson "What's in the Beaker," and it could be what's in the flask, what's in what's in the box. But it's just when I say you mix this solution with that solution, and a gas is produced or a precipitate is produced or something like that, do you understand what that means? And like, where is it coming from? What's being lost? What's being gained? What do my containers look like before I mix the two reactants? What does my container look like after the reaction is complete? During the reaction, what am I going to see? Am I going to hear anything? That kind of thing. All right, so let's talk about, let's do this reaction. Okay, so again, we're talking about aqueous systems. So this would be true of reactions like the redox reactions that take place in an acidic solution. Again, it's all based on an aqueous system. So this all pertains to the whole thing, all of Unit 2, what we've been talking about, all right? So we want to visualize the reaction that's going to occur. We want to be able to understand what's going to be observed. So like a solid forms, bubbles form because a gas is formed, that kind of thing. We want to understand what the resulting mixture looks like when the reaction's done. So what's still dissolved, what's not dissolved anymore, that kind of thing. All right, so let's do this sample question. All right, so it says, what happens when a 15 milliliter 0.5 molar solution of potassium carbonate, an aqueous ionic compound, reacts with 15 milliliters of a 0.4 molar solution of lead 2 nitrate, okay, aqueous. All right, so first let's kind of visualize what we're doing. We have this and we have that. So what does that look like? Okay, well, I have a container that has 15 milliliters of a solution, and what's in that solution? Dissolved, and I know it's dissolved because it's aqueous, and for an ionic compound, that means the ions have separated, and if I wanted to represent one formula unit of the compound, notice that there's 2 potassiums and 1 carbonate, right? So this is kind of what I have going on in beaker number 1, right? And then beaker number 2, that was 15 milliliters, and it was lead nitrate. So a lead nitrate breaks up into 2 nitrates and 1 lead, right? So this is what I got going over here. Again, these ions aren't together anymore. They've been dissolved, which means they've been separated by water, okay? And so this is what I got. This is 15 milliliters, that's 15 milliliters. All right, so what's gonna happen when I mix them together? Well, the first thing we should understand is the overall volume is gonna be around 30 milliliters. And it's just 15 milliliters of this plus 15 milliliters of that. Now, the overall volumes of solutions can change depending on attractive forces, repulsive forces, the different types of ion-dipole interactions, the size of the solute particles. All of that can change just a little bit, but it's not going to change that much. So most of the time when we do questions like this, especially on the AP exam, they'll say assume the volumes are additive. So yeah, it might not end up being 15 milliliters plus 15 milliliters. It might not end up being exactly 30 milliliters. Maybe it's 30.01 milliliters, because maybe for some reason the attractive forces cause the overall solution to expand a little bit. Or maybe it's 29.98 because maybe the attractive forces cause the molecules to get close together. But essentially, we can assume that the volume is going to be just the sum of the 2 volumes we mix together, all right? Now, we have 2 aqueous compounds, ionic compounds. We should be thinking double replacement reaction. So before we look at the equation, I should just understand potassium ions can now come in contact with nitrate ions, okay? But we know nothing's gonna happen when potassium bumps into nitrate because we know potassium nitrate is a soluble compound. And lead can now come in contact with carbonate. And we are going to get a precipitate because lead carbonate is not soluble based on our solubility rules, all right? So this is the reaction that's going to happen. The potassium nitrate is going to stay aqueous. Notice they got to put a 2 here to balance it. Okay, that's fine. But we would see solid lead carbonate precipitate out again. And, you know, on the AP exam, most of the time, I would say 99% of the time, they won't make you know your solubility rules. You know, a lot of times they'll tell you what the precipitate is. In this case, it's lead carbonate. But other times they might just say a precipitate forms. So if you had to pick, hopefully you know your solubility rules enough to know that there's no way that the potassium nitrate is going to be the precipitate. So it's got to be the lead carbonate, right? So that's our precipitate. But again, this is just a chemical equation. It's good for balancing. It's good for doing stoichiometric calculations and that kind of thing. But it's really not good to understand, really visualize what is happening when you mix these 2 things together. All right, so what will be observed? Okay, so in words, right, this solution is colorless, this solution is colorless. And so it's gonna look like we mix water with water. That's, you know, we can't see the ions, right? So it's going to look like mixing water with water. But then because lead carbonate's insoluble, it's going to be cloudy water all of a sudden because tiny solid particles will form. And given enough time, all those solids will kind of float down to the bottom because they're going to be more dense than the resulting solution. So given enough time, you know, it wouldn't be cloudy anymore. All the solids would kind of sprinkle down to the bottom, all right? So what's in the solid? Well, we know it's lead ions and carbonate ions. And what happened to the potassium and nitrate? It stayed dissolved, right? And so the way we say that is those are spectator ions, which means they're still there. They're still in the container. They're just still dissolved in water, okay? They're spectator ions, all right? So another way to look at the overall reaction is the net ionic equation. So lead 2 plus comes in contact with carbonate 2 minus, and you get lead carbonate. They react in a 1-to-1 ratio. And that's because it's 2 plus and 2 minus. All right. But what would the container look like after the reaction happened? Okay, well, we would have our solid particles float down to the bottom, and we know what that's made of. Okay, we know that the solid is lead carbonate. Okay. But we would still have the spectator ions, right? All of the potassium that we started with is still dissolved in solution. All the nitrate that was dissolved is still dissolved in our overall solution. And if we wanted to separate the solid from these dissolved ions, we would have to filter, right? We would have to pour the whole thing through filter paper. The solid would go through, would stay on the filter paper, and all of these ions that are still dissolved in the water would go through the filter paper, right? That's the whole point of filtration, right? But this is what the container would look like, and we're going to assume that the overall volume is about 30 milliliters, okay? Because we started with 15, and we mixed it with another 15, so we got 30 milliliters, right? Okay, but let's understand, this is not going to be the only thing still dissolved. There's still one more ion that I need to draw in this picture to show a complete representation of what's going to happen afterwards, okay? And that's going to be the excess ion that we had left over after we run out of the limiting ion, right? So this is why it's a good thing to know the net ionic equation and know this ratio. This is an easy one. It's 1-to-1. So what we have to do is figure out which one of these is going to limit how much lead carbonate we can get, right? If I have 5 moles of lead and 5 moles of carbonate, then all the lead would precipitate out, all the carbonate would precipitate out, and I would have nothing left over. But we probably don't have equal amounts of carbonate and lead. And that means we're going to run out of one, and the other one is still going to be dissolved, all right? And how do we figure that out? That's just stoichiometry, all right? So again, we need to find the excess ion. It's either going to be lead. We know the spectator ions are going to be in there, but we're also still going to have some either lead left over that's unprecipitated or carbonate that's unprecipitated, okay? So we got to figure out the limiting reactant, carbonate, or lead, okay? All of the limiting reactant ends up in the precipitate. So that means all of the limiting reactant is no longer dissolved, right? There's no longer dissolved ions of the limiting ion. But the excess ion is going to be, most of it ended up in the precipitate probably, but there's still some that is dissolved, okay? So again, it's a 1-to-1 ratio, and it was 15 milliliters of 0.5 molar solution of potassium carbonate. So liters times molarity gives me moles of potassium carbonate. The subscript of carbonate in this is 1, so it's a 1-to-1 ratio. So I'm starting with 0.0075 moles of carbonate, and if we do the same thing for the lead, notice the molarity was different, okay? We have 0.006 moles of lead, 2+. So which one, and they react in a 1-to-1 ratio, so it's easy. We have less lead, so all the lead is going to precipitate out. We're going to lose all the lead, but we're still going to have carbonate, right? Okay. So all of the lead precipitates. We still have dissolved carbonate ions. So what would the picture of our final solution look like? Hold on, let me do this. Okay. So the final picture of the solution. Well, obviously we have our spectator ions. We got our precipitate down there with the solid lead carbonate, and we know what that is. But we still have to draw dissolved carbonate ions in the picture because it was the excess ion. All right? All right. So we still want to be able to do all the calculations, like we still want to be able to calculate the new molarities of the spectator ions. So that's easy. If we just figure out how many moles of potassium we started with, because it's a spectator, that's how many moles of potassium we finished with, and we divide by the new volume, which it would be 0.03 liters instead of 0.015 liters, right? And if we wanted to do the nitrate, it would be the same thing. The carbonate's a little bit more difficult. We know we're going to divide by 0.03 liters because that's the final volume of whatever carbonate. But we have to figure out how many moles of carbonate we started with, dissolved, but then we have to calculate how many moles of carbonate ended up in the precipitate, and we have to subtract to get the amount of carbonate that's left over in solution. All right. And again, if you want to see how to do that or more information on how to do that, go back and watch the solution stoichiometry video. Okay. Right now we're just kind of visualizing what's going on. Okay. All right. So let's try a new one. All right. So this one's going to be a little bit more complicated. We're going to have a lot going on in this one. So again, we're starting with the same numbers. We got ammonium sulfate solution and we got barium hydroxide solution. So let's do the same thing that we did before. Okay, we're going to mix these two together. So my ammonium sulfate would look like this, because ammonium is, I have two ammoniums and one sulfate. So two ammoniums and one sulfate, dissociated, because aqueous ionic, right? And we got 15 milliliters. And then over here we got barium hydroxide, two hydroxides for one barium. So that's what this solution would look like. Okay, 15 milliliters. I got 2 times the hydroxide that I do the barium, and I got 2 times the ammonium that I do the sulfate. Okay. Now, double replacement reaction, this is what we're going to get. Okay. But the precipitate isn't the only thing that's going to happen. So barium sulfate precipitates, right? You get barium paired up with sulfate, you get ammonium paired up with hydroxide. So you get barium sulfate and you get 2 ammonium hydroxides. Okay, now ammonium hydroxide would be soluble, so it's aqueous. But, if you go back to your predicting the products cheat sheet, when we were doing the assignment, the 2-4 assignment, the net ionic equation assignment, there's something about ammonium hydroxide that you have to remember. Now, you don't really have to remember it because they'll probably remind you on the AP exam. But ammonium hydroxide, when produced in a double replacement reaction, like it is here, actually decomposes and forms ammonia, gas, and water. So really, this happens to this. So this is how we write. In a net ionic equation, we don't write ammonium hydroxide dissociated, like ammonium ions plus hydroxide ions. We actually write it like this: ammonia gas and water. So really, this is the reaction that's going on. Now on the AP exam, if they told you mix these two things, they would tell you, they would say ammonium sulfate and barium hydroxide are mixed together and this is the reaction. So they would give you the products. Maybe they wouldn't have balanced it for you, but they would tell you. And so you don't really need to memorize that little fact about ammonium hydroxide when it's produced, but understand that if you saw this, don't freak out and say, wait a minute, I thought it would have been this. Because technically, yeah, it would if you're thinking normal double replacement rules, but something happens a little bit extra with the ammonium hydroxide. All right, so this is what we got. All right, so there's 2 things we'll see, and 1 thing we'll smell. All right, so what we will see, well, we'll see the precipitate because barium sulfate precipitates. We'll also see bubbles kind of form. Now, ammonia doesn't really form bubbles when it gets formed, but anytime a gas gets formed, go ahead and say you'll see bubbles. But the real thing about ammonia being formed, as the ammonia escapes, ammonia smells. And if you don't know what ammonia smells like, eventually you'll be able to, sometime this year, we'll be using ammonia and you'll be able to smell it. And it's kind of got this kind of like a whoa smell, shock to the system type smell, which we'll talk about. It stings a little bit. But again, so the things that will be seen, precipitate, maybe bubbles, but probably not for ammonia. If it's carbonate, if it's CO2 gas being produced, or hydrogen gas being produced, or oxygen gas being produced, you'll probably see bubbles. Ammonia, you don't really see bubbles. It just kind of sneaks out of the top and you smell it. And so really the other thing observed isn't really seen, but it's smell of ammonia because the gas produces, all right? So what does the resulting solution look like, all right? Well, we got a precipitate floating down in the bottom. Maybe we'll see some bubbles, but a gas will be escaping through the top. And really, instead of seeing bubbles, we'd actually smell the gas, okay? But what else? All right, well, let's look. Let's see if there were any spectator ions. If we look at the net ionic equation, we would separate the ammonium sulfate, we would separate the barium hydroxide, but all these would stay together, solid, gas, liquid. So notice none of our ions cancel out. We don't have spectator ions. But does that mean we don't have any ions still dissolved? And the answer is no, right? Maybe not all the ammonia reacts. So if we run out of hydroxide, then the reaction stops and we'll still have ammonium. Or if we run out of ammonium, then the reaction stops for this and you'll still have hydroxide. If you run out of barium, you'll still have sulfate. If you run out of sulfate, you'll still have barium. So again, it comes down to stoichiometry, limiting, and excess reactants. We got to figure out which of these ions are going to be our excess ions and we would still have them dissolved in the solution, right? All right. So we still have to calculate what are our excess ions and what are our limiting ions. And so what I would say is look at it two different ways. So let's look at the precipitation reaction, right? The barium and the sulfate will take each other out in a 1-to-1 ratio, right? Here's the net ionic equation just for the precipitation of barium sulfate, right? So this is the calculation to figure out how many moles of sulfate we started, right? With liters times molarity times the subscript of sulfate, which is 1, will give us moles of sulfate. And liters times molarity times the subscript of barium will give us moles of barium. And just like before, we're going to have, so all, what that means is all the barium will precipitate out and we'll run out of barium, but we'll still have sulfate. Okay, so we know we still have sulfate ions dissolved. Okay, so if I wanted to go back up to this picture, I know it's safe to draw a sulfate ion in here because we know we're going to have sulfate still dissolved, but I wouldn't draw any barium because all the barium ended up in the precipitate. All right. So now let's look at that formation of a gas. So the ammonium and the hydroxide, they react in a 1-to-1 ratio as well, because +1 -1. But you don't get ammonium hydroxide, you get ammonia and water, okay? So we got to figure out how many moles of ammonium we have and how many moles of hydroxide. And this is where we got to be careful. We do liters times molarity just like we did with the sulfate and the barium. But notice in our sources of ammonium and hydroxide, the subscript for ammonium is 2, and the subscript for hydroxide is 2. So when we're doing this calculation here, it's going to be liters times molarity times the subscript of ammonium, and that'll give us total moles of ammonium that we started with, and that'll give us total moles of hydroxide that we started with. And if you notice, it's just double these numbers, right? Because we know that for every, look at this, the formula, for every 1 sulfate, there's 2 ammoniums. For every 1 barium, there's 2 hydroxides. So if we just double those numbers, we get these numbers. So this is how many moles of ammonium we have, this is how many moles of hydroxide we have, and guess what? We run, and they react in a 1-to-1 ratio, so we're gonna run out of hydroxide, but we're still gonna have ammonium left over. So we still have sulfate left over because it's in excess of the precipitation reaction, and we're still going to have ammonium left over because it's in excess of the formation of a gas reaction. All right. So all the OH minus is, and there should be an E there. All the OH minus is gone. We still have leftover ammonium ions. So what's the final picture going to look like? All right. We still got the gas being formed, so maybe we see some bubbles, but we definitely smell ammonia. We have the precipitate forming and falling down to the bottom, and we know what that's made of, barium sulfate, based on solubility rules, okay? And then we still have our excess ions. We still had sulfate left over, and we still had ammonium left over, so those are still dissolved in our solution, okay? All right, and again, it was 15 milliliters and 15 milliliters, so our new volume is 30 milliliters. Just in case I wanted to calculate the new molarity of sulfate, I would just have to figure out how many moles of sulfate are still in the beaker and divide it by the volume in liters, or how much ammonium is still in the beaker dissolved and divided by the volume in liters, 0.03 liters, all right? All right, so hopefully that, I don't know, helps you. Maybe it's something you already knew, I don't know. But, you know, being able to visualize very simply, right? This is, you know, my daughter in, you know, 3rd grade could probably draw this, you know? So this is not very complicated, and it's a good way to visualize what's going on when, especially when you're mixing things together in an aqueous system. You really want to visualize the ions that are in play. The ions or the different dissolved molecules or whatever, all right? So hopefully that helps you out as you review for the Unit 2 test. And yeah, that's it. Have a good one.